Hello, today we are going to discuss about AVL tree. In binary search tree, we have observed the worst case complexity to search an element is big O of n, where if we have the elements like 10, then 20, then 30, then 40, if the elements are coming in either ascending or descending order, then this structure is called skewed tree, or this is called skew tree, skewed structure. This is called right skew, and then it is also possible left skew. So, in that case, the time complexity for worst case to search an element, that is big O of n. So, that is a problem. So, what we perform? We just go for some kind of balancing the particular number of nodes. That means, we are having a particular root node, we are trying to distribute whatever elements we are trying to store, we will distribute among its left subtree and among its right subtree. So, that height of the balance search tree will not be more than log n. So, by this we can able to balance the tree. So, the three persons Adelson, Velsky and Landis, they developed a mechanism by which we can able to fix, or we will not make it the increase the height of the balance search of the particular tree not more than log n. So, by their first name alphabet, the name is taken AVL tree. What are the different applications? There is huge applications actually, like in database indexing, optimization, and we are having in memory, set, and in dictionary also. There are different places where we apply this particular AVL tree. Now, in binary search tree, we have a concept that is called balancing, and we have a concept that is called balance factor. What is balance factor? So, if I have a value that is balance factor. So, what is this balance factor? Balance factor means the height of the left subtree. What is left subtree? So, whatever the tree is there, this part is called left subtree and this part is called a right subtree. So, if I consider the height of the left side subtree is h1 and height of the right subtree is h2, and what is the balance factor of this particular node? The balance factor is h1 minus h2. And what are the values that is allowed in AVL tree? The values that are allowed, this will be either 0 or minus 1 or 1. That means, the difference of the height between the left subtree and right subtree will be not more than 1. It will be either 0 or minus 1 or 1. So, here if we have a particular tree, binary search tree, then if we try to calculate the balance factor for each node, then how we will calculate? Look, if I have a 5, if I have this element 5, for 5 there is no height in the left, no subtree in the right. So, it is 0 minus 0, this is 0. So, balance factor of 5 is 0. What is the balance factor of 7? 1 minus 0, that is why it is 1. For 8, what is the height of left subtree? This is the left subtree, this is the left subtree. So, height is 2. So, this is 2. What is the height of the right subtree? 1, 2, 3, 4. 1, 2, 3, 4. Okay. So, this will be 4. So, what is the value? That is minus 2 is the height of the this particular node. What is the height for this one? For 2. So, it is left. What is the height? Left subtree 1, 2, 3. 3 minus 0. This is 3. For 15, what is the height for balance factor for 15? Balance factor left is 0, right is height is 2. So, that is minus 2. So, for 7, this is 0 minus 1, this is minus 1. For 18, 0 minus 0, this is 1. So, this is problematic, because whenever we are trying to search, then that will be difficult, that will increase in worst case, that will be big O of n to search an element or the height of this kind of trees. So, in AVL tree we rotate. If the height is increasing, like in this side the elements are more, we will just make them this side. If the height or in this side the elements are more, then we will move the element that side, that is called rotation. In binary search tree, we will make some rotation, and by help of some rotation, we will move some elements in another side, and that way we will perform or design a new tree, and that is called self balanced binary search tree, or that is also named as AVL tree. Let us have a look. There are four different cases or four different imbalance cases: left imbalance, right imbalance, left imbalance, right imbalance. Say for example, we have some elements like 50, 30 and 10. We are trying to insert them. So, 50 will be inserted here. So, what is the valence factor for 50? 50 is left subtree is 0, right subtree is 0, 0 minus 0 the height, okay, then 0, no problem. We will move forward. 50 is inserted already, then 30 will be inserted of its left node. So, 30 is here. What is the valence factor here? So, this is 0 for 50, this is 1 minus 0, this is 1. Now, no problem, till now there is no problem. Now, we are going to insert 10. So, 50 is here, 30 is here, then 10 will be its left side. So, if I calculate the valence factor for 10, this will be 0 minus 0, this is no problem, this is 1 minus 0, this is 1, this is 2 minus 0, this is a problem. What are the values allowed for the balancing factor value of a particular node? That is 0, minus 1 or 1, but here it is 2. So, the problem is here, problem we have for this particular node, the problem is arising. So, this particular problem is left imbalance, because from where the problem arises this, then from that we will go to the path where the element is inserted. So, the direction is left and left, that is why it is called left imbalance. So, what we will do whenever we are having some left imbalance, we will rotate, if left side is the problem, we will move the element to right side. Then what we will do? We will just rotate this tree and making 30 fix, we will make down 50. Okay. So, 30 will be here and 10 will be here and 50 will be here. So, look, after rotation the tree is still binary search tree, but we are having the height which is balanced, which is not more than log n, and the left side is lower, right side is higher element. For right imbalance, have a look the examples, the elements which we are going to insert, that is 10 we are going to insert. What is the valence factor values for 10? 0 minus 0, this is 0, no problem. Next, 10 is there, what element we are going to insert? 50. So, 50 is here. So, we will have this is 0 minus 0, this is 0. For 10, left side is 0, right side is 1. So, 0 minus 1, this is minus 1. Okay. So, for this no problem is there still now. Then we are going to have 10, then 50, then 70 we are going to insert. So, 70 is here. So, as 70 is here, now we will calculate the valence factor values, 0 minus 0, this is 0. For 50, 0 minus 1, this is minus 1. For 10, this is 0 minus 2, this is minus 2. So, what is the problem? There is minus 2 is the problem. We know we do not want minus 2 value as valence factor. So, what we will do? We will rotate. So, where the problem arises? The problem arises here at 10. From 10, we will move towards the element we have inserted in that path, and that is why it is called in right side. Again we are moving right side, that is why the problem name is called right imbalance. For right imbalance, we will move or rotate the element, making 50 fix, we will rotate 10 in left side. That is, if that side is heavy, we will just move it to left side. Then 50 is up, 70 will be as usual place, and 10 will be left child of 50. Now, look, by this way all the elements I have rotated, I have make some one rotation, and by help of the single rotation we have the balanced binary search tree. 50 left child is 10. So, always remember after rotation again the tree will be binary search tree again, only we are changing the arrangements for this case. So, for this case have a look, left right imbalance. So, in case of left right imbalance, so 50 is here, for 50 no problem, 0 minus 0 0. Then we have inserted 50, 30 is here, 30 is here. For 30 this is 0 minus 0 0, for this 1 minus 0, this is 1, no problem. For whenever 50 is there, then 30 is there, then what is inserted? 45 is inserted. 45 will be right child of 30. Now, what are the balance factor values? Let us calculate. This is 0 minus 0, this is 0, this is 1 minus 1 minus, sorry, 0 minus 1, 0 minus 1, this is minus 1, and for 50 this is 2, 2 minus 0, this is 2. So, problem is here. So, where the problem is? Problem is here. From that place we will move towards the element that we have inserted, and what is the direction? This is the left side and we are going to right side. That is why it is called left right imbalance. For left right imbalance there are two rotations are required. First we make the problem into left left imbalance. First we make the problem into left left imbalance. For left left imbalance what we do? For left left imbalance what we do? We will move this element here. So, 45 we will be moved in this place and 30 will be down. So, 50 is here, then 45 and then 30 will be down. So, this is one rotation here, then another rotation is required. Now, the problem is left left imbalance problem. For left left imbalance problem we will move this element here. So, 45 will be up, then 30 will be here and 50 will be here. Now, this way we have balanced the tree. Okay. Now, for this case, now what are the elements? What are the elements? 20 is here, 50 is here, no problem. For 30, when we have inserted 30, so 20 is here, 50 is here, then 30 is greater than 20, lesser than 50. So, for this case the balance factor problem is there. So, this is 0 minus 0 0, 1 minus 0, this is 1. For this is 0 minus 2. So, that is why it is minus 2. So, here is the problem. So, we will make the direction. What is the direction? This is right and we are coming left. This is right side, this is left side. That is why it is called right left imbalance. So, for right left imbalance what we will do? We will rotate the 30 up, we will move this element and 50 will be down. One rotation, another rotation will be required for solving the right right imbalance problem. So, first 20 will be here, 30 will be here and 50 will be here. Now, the problem is right right imbalance, To solve it, what we will do? We will simply right right imbalance. So, we will move this one. So, lower rotation then upper rotation. Okay. Then we will make 30 here up, 20 down and 50 here. Okay. So, by help of this we will